Today we'll continue with our part two. So how to analyze the three-phase balance circuit. So this is the part two of this video series. If you've not watched the part one, I'll leave the part one in the upper right hand corner of this video. Kindly make sure that you watch part one. If you don't watch part one, you will not be able to understand what we are really doing here, because I explain all the formulas I'll be using here and how to derive the formulas in part one. So kindly watch part one before coming to watch part two. So without wasting much time, please remember to like, share, and subscribe for more content like this. So let us start. So with our next problem says the input voltage, current, and power to a motor is measured as 400 volts, 12 amps, and 4 kilowatts respectively. Determine the power factor of the system. So here we realize that the question didn't state whether it's a delta or it's a star. And I told you in our previous video, the part one, that when a question doesn't state whether it's a delta or a star, we assume that it's a star. So we don't care. That is what we do. We just assume that it's a star. So since we are assuming that it's a star, we have to calculate the power factor. They are telling us that we should calculate the power factor. So for star, this is the formula. I gave this formula in our previous video. So since we know the line voltage, which is 400, we know the current, which is 12 amps, and we know the power, which is 4 kilowatts. This is real power. So that's why we are using this formula. What we don't know is cos phi. The cos phi is also known as the power factor. Cos phi is equals to power factor. It's also known as the power factor. So since cos phi is known as the power factor, we can make cos phi the subject. Making cos phi the subject, we get this equation. Then we just substitute our power. Our power was 4 kilowatts, so it is 4,000 divided by root 3 times our line voltage, which is 400, times the current 12. Then we are getting our cos phi as 0.48. So we can maybe approximate it to say, let's say 0.5. So that is how to simply calculate our power factor. So let us take our next example. So with this, our next example, this is a Y connected impedance. A Y connected impedance. That the Y simply means a star connected impedance. Z1 is equals to 20 plus J 37.7 per phase is connected in parallel with a delta impedance Z2. This is the delta impedance. The Z2 is the delta impedance per phase. For an impressed three-phase voltage of, this is the line voltage, 398 line to line. Compute the line current, power factor, and power taken by the parallel combination. So to start with, we said when you are given a question and one of them they are in parallel and one of them is in delta, you change the delta to star, and we change the delta to star by dividing the delta by 3. So we change Z2 to star by dividing it by 3. So changing it, we change this one and divide it by 3. So changing it and dividing by 3, we get 10.0 minus J 53.1. So doing that, we now need to now calculate for our our phase voltage. So to calculate for the phase voltage is simply for we now apply star. So we are now applying star. So the star for formulas, we said phase voltage here is equals to line voltage is equals to phase voltage times root 3. So to calculate the phase voltage, we simply divide the line voltage by root 3. So phase voltage is equals to the line voltage, which was 398 divided by root 3, and we are getting 230 volts. Then after doing that, we now need to calculate the phase current. We know the impedance. We know the impedance of both of them. So we just uh, we now, since we've now converted them, we just add the impedance Vp. The Vp is 230. 230 divided by the 20 plus the 37.75, because Z1 divided by Z1 plus Vp divided by Z2. So that is what we do. Then after doing this mathematics, we simply get 3.37 angle minus, it will give you your angle. If you want, we can also leave it in the rectangular form like this. Then we've now found our IP. IP is simply equals to 3.37 amps. Then we know that for star, IP is equals to IL. The phase current is equals to the line current. So we just state it as the IL is equals to 3.37 amp. And after doing that, they said we should also calculate the power factor. So how do we calculate the power factor? We calculate the power factor by um, taking the angle. So we know the angle here, which was 9.9. So we just say power factor is equals to cos of the phi. So cos of 9.9, we get 0.985. So lagging. And to now calculate, they said we should compute the power taken by the parallel combination. So we have to calculate the power, that is raw power. So we just invoke this formula. This is our formula. We know the line current, the line voltage, we know the line current, and we know the power factor. So we just multiply them here, and we'll get our final answer as 2.29. This is how we simply solve it. You see, here the tricky part was that you have to convert the delta to the star. After converting the delta to the star, then you are good to go. You can now apply your star formulas to simply calculate the phase voltage and line current, and finally come and calculate the power factor and the power consumed by the parallel combinations. So we'll take our next question. So with our next question says a star connected motor is connected to a 400 volt three phase 50 hertz line. The motor produces an output of 2681 kilohertz at an efficiency of 93 and a power factor of this. Calculate A, the active power absorbed by the motor, B, the reactive power absorbed by the motor, and C, the apparent power supplied by the transmission line, and D, the line current. So for A, to calculate the active power, so the active power is also known as the power input. Since we know the efficiency here, we just use the efficiency formula. Efficiency is equal to input power over output power. So we now need the input power. So changing subjects, we get our input power as 288 kilowatts. Okay, 2883 kilowatts. And afterwards, they said we should calculate the reactive power. So here's just formula work. What was the reactive power? Reactive power is Q, right? So we, but first, before we calculate reactive power, we have to first of all calculate the apparent power. And the apparent power was equals to the power divided by the power factor. So doing that, we have our P in. We divide to calculate for the apparent power. We have our P in divided by our power factor. So P in is 2883 divided by our power factor of 0.9. Then we get our apparent power as 320 3203 kVA. Please, the units are very important because the units will tell you the kind of power you have calculated for. And afterwards, we now need to now calculate the apparent power. So with the C, this is the C, we've already calculated the apparent power. Then to now come and calculate the reactive power, we come and code this formula. Reactive power is equals to the apparent power square minus the real power square, the P in that we just calculated. So we just do our change of subject there to calculate, that is our 3203 square minus our 288 square. Then we'll come and get our reactive power. And reactive power, as we said in our previous video, that it was measured in VAR. So it is equals to 1395 kilo VAR. Afterwards, we've now calculated already. The C was that we should calculate for the apparent power, and we calculated for the apparent power using this formula. So this was the apparent power. So this is the apparent power. So that was the formula we use. So we just come and write it down. That is for the C. And the D said we should calculate the motor line current. So the motor was connected in star. So we now need to calculate the line current. And we know that for star, we can calculate the line current by using this formula. I stated this formulas in the part 1 of the video already. So the line current is equals to the apparent power divided by root 3 times the line voltage. So you simply multiply it. After multiplying everything, we get our line current as 462 amps. So this is how we use our formulas to simply calculate our uh, active power, reactive power, apparent power, and the line current in three-phase circuit. So please, Thank you very much for watching up to this time, and kindly like our video, share and subscribe for more contents like this. I think this is our last video series on uh, three-phase circuits. Three-phase circuit is very simple. It's just a formula work and a little bit of logic. There's nothing really complex about this three-phase circuit. So take your time and really go through the questions. Try to really solve the questions on your own before proceeding. So, so thank you very much, guys, and kindly remember to like, share, and subscribe for more contents like this. So please leave your comments and leave suggestions on how we can make the videos better for you to understand. Bye.